Hello everyone, good morning. My name is Kamal. I'm a software from WhatsApp Dev Infra. In this keynote, I'd like to share some experience on how we build code analysis at WhatsApp, including some challenges we've encountered and the design choices we've made, which may be helpful to the community. This talk will also cover some industry practice on continuous integration for shift left back prevention. This talk contains joint work with WhatsApp and Meta Dev Infra teams, where we deliver CI solutions. We work on, we do research and development for code analysis, and we work on dev tools, for example, testing frameworks and IDE support for dev efficiency. I'm going to organize this talk as follows. First, an introduction to some background knowledge, followed by an overview of code analysis tooling at WhatsApp, and then I dive into some technical details of dynamic and static techniques. Each will include one example system we have deployed at a large scale. And finally, I'll talk about the DevOps practice and our CI process for raising high quality signals to our developers. So WhatsApp is one of the most popular and the largest messaging app in the world. The app is owned and operated by Meta. So currently, over 2 billion users in over 180 countries use WhatsApp to stay in touch with their friends and family. At WhatsApp, our core value is about reliable, secure, and private messaging. We aim to build the most private and robust communication service available. This means we have critical requirements around how to ensure safe changes, and meanwhile allow our developers to move fast for deliver new features to users. At the core of WhatsApp, we have two primary components, the client and the server. So together they provide a unified experience. The client captures end user interactions while the server ensures these moments of connections are delivered safely and reliably. Privacy, one key feature is end-to-end encryption, which is the foundation of WhatsApp private messaging. It helps ensure that only you as a user and the individual that you are talking to can read or listen to the messages, and nobody in between, not even WhatsApp. It's crucial that our code analysis can cover both client and server-side code, and including their interactions for a seamless end-to-end user experience. On server side, to handle the scale of billions of users and their daily message delivery, the server has to evolve its architecture continuously. Like many large services, WhatsApp employs a microservice architecture for the benefit of reliability and also scalability. Here's a brief overview. So WhatsApp server is powered by Erlang. It's composed of millions lines of code. In this figure, the small rectangles, they represent Erlang node. They spread across many small microservices and together form a large geo-distributed Erlang cluster. So the server has relatively decoupled architecture, benefiting from the nature of microservice, because by definition, microservices are small independent processes that run isolated processes. So basically, WhatsApp breaks down its functionality into many small functionalities. For example, the chat nodes for managing client connections, and the group nodes for managing group chat, and account node for managing account info and device info. So one of the biggest advantage of microservice architecture is the ability to scale independently. For example, let's say if there is a surge in media sharing service, one can easily scale up the related media processing service and don't need to worry about unrelated ones. Although microservices also have a bunch of other advantages, they also introduce some complexities. For example, in areas like service node discovery and continuous deployment and monitoring of the services. However, at the scale of billions of users, the benefit on maintainability and scalability may outweigh their challenges. On client side, code analysis techniques have been widely studied in academia. There is a perception that the client side research has gained significantly more attention in the past years compared to server-side analysis. One potential factor might be the client-side subject, especially mobile apps. They are very visible and accessible in the ways that the server-side code is not. So the client-side research had been applied to detect multiple types of issues like reliability, correctness, security, and privacy. So at WhatsApp and Meta, such techniques have also been largely deployed. For example, one platform is called Cpings. We have deployed the automated client exploration at Facebook since 2017. Handling a large number of code commits requires a structured approach for code quality and also coordinating team collaborations. So code analysis together with other testing and verification jobs, they play a crucial role in helping both commit authors and also the reviewers gain confidence in their code changes. So considering that efficiency, it's preferred to have rapid feedback as early as possible in the development life cycle. Ideally, we want every signal happen during diff time and inline at source changes. So as we know, a bug is much harder to investigate and fix when you lose the diff context after landing into chunk. In practice, this kind of requirement introduced non-trivial challenges to dynamic and static code analysis techniques. For our practice, it won't be acceptable if we block developers and ask them to wait for machine signals for an unreasonable amount of time. As we've seen from the introduction, we have a good set of non-trivial challenges and interesting problems that code analysis may help to solve. Now let's take a closer look at the tooling that we have. As mentioned, WhatsApp server is written in Erlang at the scale of millions lines of code. To handle such a large and fast evolving code base, we perform a combination of dynamic and static code analysis. For dynamic, I'll reserve for a separate section later. So static tools are very popular in our Erlang repo. We use them to scan every diff submitted by developers. First, we have linters. They are lightweight checkers, which are useful to enforce coding conventions and also helping developers to make best practice suggestions. And then we have XREF, the cross-reference tool provided by Erlang'23. We found it very useful to find app dependency issues. We customize the tool to fit into our build process and also continued integration. Then we have quite heavy usages of dialyzer, which is effective in finding multiple types of issues like tab errors or dead code. In practice, we give it very high priority and ask our developers to write specifications and fix the bugs reported by dialyzer. One challenge I mentioned earlier is that the time to signal during diff time, as dialyzer could be quite slow when running against a huge code base. So we invested some effort in enabling incremental mode of dialyzer, which means we allow us to reuse the intermediate analysis artifacts from dialyzer from base revisions. And later when we do diff analysis, we can reuse those base artifacts. This work we have open sourced and we contributed back to the OTP repo. It has been already released together with the recent OTP 26. More recent work we have also open sourced is Equalizer, the type checker for Erlang. It aims to tackle the static typing challenges for Erlang similar to other languages like Py for Python and Flow for JavaScript. Today, Equalizer is running on our entire server code base and helping developers to move fast with static type hints and checker signals. Last but not least, we have Infer, which is also developed at WhatsApp and open sourced. Infer fills the blanks that the previous tools, they do not check user-defined properties. For example, we have some requirements on data flow analysis. So basically, Infer has been deployed to regularly scan our code base for finding both reliability and customized properties. I'll elaborate on the technical details in a later section. For client-side analysis, we also perform a combination of dynamic and static code analysis, and they support popular tech stacks like mobile platforms of Android and iOS. Typical examples are linters and Infer static analysis, where the Infer is a generic static analysis platform we used and also extended to Erlang. We onboarded Sapiens for dynamic analysis and testing at WhatsApp. To better understand the goals of client-side tooling, let me give a quick motivation example. We all know that mobile apps sometimes can crash, and this annoying experience, it interrupts a user journey and may cause data loss. If you use Android devices, you may be familiar with this screen of app crashing message. A crash is basically a fatal system failure, which usually indicates an underlying bug of the app. And one prevalent cause is non-pointed reference. We want to help our developers to catch these kind of bugs as early as possible in an automated way. So Sapiens is the main techniques we have iterated at Meta and onboarded to WhatsApp. It performs fully automated client exploration to support analyze client runtime behaviors. The development covers both Android and iOS code bases at WhatsApp. Sapiens generate system-level events that simulate user interactions in order to find faults. You might be familiar with random fuzzers, which are good at performing random search like Android Monkey, but the general test can be inefficient and unrealistic. On the other end, we have human testers who are very good at designing test input, but it's a tedious and slow task. Sapiens performs smart search for generating input. It sees the sweet spot between the two ends and performs automated mobile test generation. And we are pushing the boundary to the right end, trying to make the strategy more like human, but meanwhile remain fully automated. On static analysis, Infer is the main platform we developed at Meta and also adopted by WhatsApp. So Infer supports multiple language front end, for example, C, C++, Objective-C, Java, and most recently we added Erlang support. It supports over 20 analyzers in the backend to detect different types of issues, for example, memory safety, data races, time complexity, deadlocks, and temporary properties. Infer is also open sourced. You'll be able to find the technical details in its GitHub repo and also the publications. Next, I will do a deep dive about the dynamic analysis for Erlang, including some technical designs and our implementation of an example system called Foster. In academia, input generation has been a hot topic in the past decade. There are hundreds of studies have been published for client automation. If you search about automated Android testing and analysis, you'll get a series of papers asking the question, are we there yet with all these techniques? Despite the controversial answers, the problem of client-side analysis is relatively well understood. When it comes to server-side, if you search about like server automation and analysis, you likely get the similar set of results because the client analysis are so popular. To enable effective server-side analysis, we need a comprehensive set of input to drive the program behaviors. One common approach that has been widely practiced is record and replay. However, recording from production doesn't guarantee privacy. In our scenario, we need approach that do not record any production data and don't replay user data. So we proposed the Foster project for this. It's a privacy-first dynamic analysis platform that generates server traffic seeking to cover as many program behaviors as possible. We have a few principles of our approach. First is privacy safe, meaning we are not doing intrusive changes to production. And we don't replay any user data. Instead, we simulate user traffic, including their interactions. And we perform most of our analysis in isolated, controlled sandbox environment to avoid side effects from being introduced to production. FOSTA is short for fully automated server testing and analysis. With continuous generation, it doesn't require human engineers to write and maintain the general test input. We published our FOSTA work at the ISST 2022 conference. It has the honor to receive a Best Industry Paper Award. The FOSTA application scenario has three major use cases: reliability testing, privacy analysis, and performance analysis. The first two use cases have already been widely deployed at WhatsApp and integrated as part of our CI pipeline. It analyzes every diff of our code base before merging into chunk. So this figure shows overview of WhatsApp server traffic to help understand how FOSTA works. Traffic is bidirectional between client and server. And these connections can be enter-encrypted or not enter-encrypted when routed through a vendor. A client may establish enter-encrypt connection with client B or organization, and the organization may programmatically send or receive messages via server-exposed APIs. And as introduced earlier, WhatsApp server contains many microservices, and some of the backend are non-WhatsApp. For example, WhatsApp Business API heavily depends on Meta backend. So this means from FOSTA's perspective, we need to care about not only client-to-server traffic, but also server-to-server traffic. To simplify, here I'll only cover the client-to-server pipeline. The traffic between client and WhatsApp server follows the XMPP protocol, which is short for Extensible Messaging and Presence Protocol. The message between client and server can be described in XML-like format. Here shows an example showing such traffic data carrying the latency info of IP addresses. And XMPP calls such data as message standards. The spec has basically the spec has the same structure with the standard. In the example here, the spec latency indicates the attributes should be integer between range X and Y. And such specification is critical to FOSTA not only because of realism, but actually according to RFC, a server may validate the client's and data structure and validate. Any malformatted ones may be rejected by server. This will lead to missing coverage for FOSTA. Let's see how FOSTA generates traffic based on the specifications. FOSTA needs to generate multiple types of traffic depending on the target use case. Realistic client traffic is that is similar to production, may be used to ensure critical user journeys are handled as expected. And this may also be used for realistic performance regression detection cases. And second, unrealistic traffic may be used to exercise corner cases of our program behavior. This may reveal crashes that may lead to security or privacy concerns. On privacy, we intentionally to synthesize traffic with artificial personal identifiable information known as PII. We inject this PII into our system and trace their propagation for checking privacy leakages. Next, I will go through this overview of FOSTA architecture, which have three major components: the policies, which mostly configuration, and traffic generator, and the signaling pipeline. The input composed of three types of configuration. First, traffic specification, and second, domain knowledge per use case, for example, the PI configs and standard distribution. And third, we have codified policies which are used to instruct Foster which types of error to detect. The output of Foster is either to comment on developer's diff or raise a task with required actions to help developer fix. To start with, the spec parser, they take the traffic specification as input and pass the specification to a data generator, which would initialize some traffic. And then the strategy module optimize this initialized traffic and send to a rate player module, which would convert the generated traffic into a client readable format. And then the rate player would send this traffic to instrumented services, which were automatically compiled from transformed source code for like tracing the coverage or tracing the call stacks of the runtime behavior. And then we have two detectors. The Oracle detector basically check the runtime behaviors against the codified policies and record any violation detected. Then we have the coverage collector, which collects the line level coverage driven by our generated input. And this fitness, together with like call stack traces, they form as fitness values, which would be sent back to the stretch module to guide the search, which may be evolutionary. And for the output, the report generator would generate a comprehensive bug report to help developer debug and fix. And this report contains stack traces and code pointers, and also suggested actions to help developer reproduce the bug. Foster has three strategies. First, bias random, and second, Markov chain, and third, evolution search. Bias random, we intentionally to generate both valid and invalid standards. However, we may give a higher weight for generating more realistic ones for considering the coverage. Markov chain, we gather aggregated sampled standard data into a frequency distribution and build a Markov chain. The idea here is to generate traffic that has a similar profile to production. Evolution search, it is capable of optimizing multiple conflicting objectives, for example, in maximizing code coverage and meanwhile minimizing the traffic size. In our early study, we have demonstrated convergence of multiple conflicting objectives. One weakness of the three fully automated strategy is that they don't well consider inter-standard dependency. This may miss some server state, and Foster complements this by using an approach called guided flows. The idea is pretty straightforward. Let me show an example here. In this example, basically, it shows a valid call offer and response workflow. Let's say Alice tries to call Bob. First, Alice needs to send a call request standard to Bob with a call ID 1235 at the top. And in order to make the call go through, Bob needs to send an answer core standard with the same call ID. So basically, the guided flow helps us to ensure this meaningful call ID is inserted to the right place when we construct the standards. So the listing here, basically, in line 2, we randomly generate some call for IDs, and subsequently, we insert call ID to the right places. Note that partial spec are still randomly generated. This is for the consideration of increasing coverage and the diversity of our generation. Next, let's evaluate how Foster approach performs in a practical setup. Foster has been deployed at WhatsApp for more than 2 years already. In the Foster publication, we evaluated its reliability use case. We answered 3 questions. First, does Foster found any real reliability issues with its generative traffic, and do our developers fix them? And second, what are the most common error types reviewed by Foster? And third, does the coverage improvement lead to the fact that finding more unique errors? To answer these questions, we analyze Foster metrics collected from 1 year deployment, including errors detected, fix applied by developers, and computational cost, and also fix detection via automated analysis, and also semi-automated analysis by talking to our developers. We also check developers' reaction to we also check basically we talk to our developer to understand the root cause that why they do not fix the reported issues. A natural starting point for our evaluation is the numbers of errors detected. In total, Foster found over 1,800 unique errors in 1 year deployment period. This translates to around 8 unique errors per workday. And note that there are like these step changes in the rate of error detection, and these are caused by continuous improvement of our architecture, our infra. For example, by introducing a new runtime environment or introducing new strategy. For the reported thousands of unique errors, Foster was able to, on average, finish in 25 minutes. For end-to-end time to signal. This is actually quite reasonable compared to similar CI jobs during diff time. And regarding developer fixes, we found a high fix rate of 74%. This is also quite competitive compared to similar fully automated tools. To understand the cases that were not fixed, we did a manual analysis, and we found the missed cases are usually due to false alarms. And one major factor to contribute to our false alarm is the popular Erlang paradigm, let it crash. So basically, as we know, the let it crash paradigm is very important for ensuring resilience of the service. But on the other side, it can easily cause some misalignment between human intention to let it crash and the system specification may not want it to crash. So there are some misalignment which cause some troubles in our analysis. One of the unique contribution of industry report on code analysis is the fault distribution from closed source industrial production. We can see here the top two categories of errors were caused by the Erlang pattern matching mechanism. 33% of errors were caused by either function level or case level pattern mismatch. And we found 14% crash report. There are general Erlang crash report, which may also relate to the root cause of pattern mismatching. And we found 9% of errors, there are soft errors, they are logged by developers and handled in the system. Note that this result is very Foster and Erlang specific and may not generalize. So one controversial question for both academia and industry is whether code coverage correlates to stronger fault detection capability. This figure shows that higher coverage did correlate to the fact that Foster catching more reliability errors. And to further support this correlation, we did an end-to-end experiment. During 1 month period, we ran 2 versions of Foster on every published diff, and the base version and the improved version with 2.3x on coverage. And we then compare their detected errors. We found the additional coverage contribute to around 40% detected issues, which would otherwise be missed without the additional coverage. So this confirms the importance of code coverage, which we are continuing the improvement. A quick summary of Foster and its reliability use case. So Foster is a privacy-first spec-based traffic generation system. It's fully integrated into MetaCI pipeline and providing fast diff time analysis for shift left bug prevention. It has detected over 1,800 unique reliability issues with a fixed rate of 74%. In practice, we found dynamic analysis techniques, they are in general very useful with very powerful, strong fault detection capability, and meanwhile it can maintain a low false positive rate. However, one major limitation is about coverage. It heavily relies on the input generation strategy to generate a comprehensive set of input that can drive different program behaviors. To mitigate this risk, we perform static analysis that aims to scan all code paths, including those are rarely executed code segment. However, the one major trade-off is that a static analysis may be prone to false positives without runtime context. At WhatsApp, we use the static analysis to infer to help developer catch bugs early in the development lifecycle. For WhatsApp server analysis, we extended infer to support the Erlang language, which is named as infer, meaning the Erlang version of infer. Here's a very high-level overview of infer platform. The static analyzer support front end for multiple languages, as I mentioned earlier, like Java, C++, and Objective-C, and most recently we add the Erlang support. And this front end would convert the source code into a shared intermediate language. And then this intermediate language will be sent to backend analyzers for detecting multiple types of errors. Specifically for Erlang, we use two of infer's backend analyzer, which are called Pulse and Turbo. So infer's methodology basically they involves a compositional analysis to create summaries of the individual functions based on separation logic. In general, it tends to under-approximate in order to reduce false positives, but sometimes may also intentionally to over-approximate to reduce for the coverage of true positives. Infer runs in CI and can report inline signals, pinpoint to a line of the root cause. For example, here shows how the signal may look like. Here it found a non-dereference and pinpoint to the location where the issue is. I'll dive deeper in a CI section to talk about how this process works. For the reliability use case, infer is good at catching pattern mismatch issues. For example, here's head function at the top, and below we have a bunch of other function calling head and perform pattern matching. The good function will succeed and the remaining will crash because of mismatch. So we run infer with the Pulse analyzer and take this piece of Erlang code as input, and then we can see all three pattern mismatch issues were captured by infer. In addition to the demo case on reliability, infer also support other data type errors, for example, accessing non-existing keys in a map. And this kind of type errors are similar to what dialyzer or equalizer may also detect, so they are not the main focus of our analysis. A more interesting use case is tent analysis with user-specified properties. So it tries to answer the question, does the source data A flows to any sync function B that are interesting? This kind of requirements can be represented by automata, where we loop in a start state to be able to track multiple values. And then if we see a call to the source function, we mark its return value as being dirty. And later, if we see any of this dirty value flows to a sync function, we turn into an error state. This approach has a limitation is that it only tracks exact values and may not support transform data. In practice, data transformation is a very important feature we need to cover. For example, let's say we need to find all the code path where some sensitive numbers are stored in database. And such data are interesting even in transformed format, for example, only keeping last 4 digits. Such requirement can be defined as the extended version of the automata, where with the non-deterministic path. And such automata can specify the behavior that our analysis should look for. And we added Erlang support for register data transformation functions. Another challenge is that Erlang has a variety of widely used built-in data structures, for example, list and map. Infer has support for data structure. However, in other language, this unbounded structure is usually modeled with approximations. So we added support for Erlang accordingly. For example, maps are modeled with recency abstraction, where only the latest key value pair is stored. So this kind of approximation is important for improving the precision of our intent analysis. The Erlang Infer architecture contains 2 major phases. First, a capture phase, which would take the source code and convert into intermediate representation. And here, note that the input contains both ODB specification and the Erlang code subject. And here, the ODB library specification would make the analysis more precise. And then we use O compiler to transform the source code into Beam files, including their abstract syntax trees. And second, the analysis phase, we run different backend analyzers. And here we run pause and topo for Erlang use cases. And finally, the reported issues are reported through the CI pipeline. To help deploy our newly developed static analysis with high quality signal, we created over 900 small functions to cover Erlang language features and the corner cases. These functions were designed to either successfully terminate or crash intentionally. We have performed an actual cross-check as Oracle based on the agreement between compiler result and infer analysis. A quick summary on static. So we deployed infer to provide scalable and extensible static analysis for Erlang. It detects reliability issues and user-defined properties via intent analysis. And we added Erlang front end and extended the backend analyzer, pause, and topo. We also deployed infer to WhatsApp Server CI and open sourced our work as part of the infer platform. So both dynamic and static analysis have their strengths and limitations. So we explored a bit on the combination approach to see whether it can give a better performance. In general, infer is quite good at the scaling. However, this is sometimes achieved by giving up on complex functions. And this may lead to too much over-approximation. This may lead to too much end-approximation. And as a result, it may make some true positive bugs. So the idea here is that we can leverage Foster's runtime observation and help infer with actual context information. We implemented this idea, and here shows an overview. We first run Foster traffic generation, and then run also developer-authored test to trigger some complete runtime behaviors of complex functions. And then we log the execution traces, including the input and output pairs of the functions. And later, when infer analyzed the complex functions, we directly used observed pairs directly instead of doing the inference. We have made some initial evaluation and found this combined approach is more effective than running each two independently. As we have demonstrated, dynamic and static analysis, they are very useful for revealing code risk early. Next, let's talk about how to deliver bug signal to our developers effectively and timely. This is where DevOps and CI come in. Here shows an overview of how continuous integration works at Meta and how code analysis increases automation level. So on a high level, we run code analysis continuously to scan both WhatsApp server and the client code bases. When an engineer make a change to WhatsApp, a diff needs to be submitted to the code collaboration platform, which is named as Fabricator. And then it will trigger CI jobs, and it will be reviewed by at least one human engineer, and it will then get merged into chunk if it passed the CI verification and also human review. We run this diff time. We run this process for diff time, and also we schedule a bunch of master job to analyze continuous build. A more specific example is Foster's integration. Let me dive deeper and show more detailed components. So on diff submission, the change will trigger job of target determinator. And this job, the main purpose is to perform change impact analysis that would decide a minimal set of CI jobs to be scheduled for saving computational resources. And then we run test selection, which would select manual written tasks that are relevant to the code changes. And for Erlang, we need to make a diff build. For Foster private use case, we have a tent compiler that instrument sync APIs for tent analysis. And then we run a combination of testing and verification job, including Foster, as part of the testing and verification jobs. And if any of the job detect any errors, they'll go through a photo localization process and signal boosting, and then triage to the diff authors. This process may be iterated several times until the CI signals are green on the diff. To verify the health of chunk, CI schedules continuous testing and verification job periodically, including Foster's analysis. A healthy chunk revision further triggers a continuous deliver job, which would release the code changes to end users. Diff time signaling is one key step to further shift the regression detection and fix earlier. But on the other side, diff time detection is a hard problem because of the constraint on computation resources and also signal quality. Foster is quite efficient to finish from end to end. As introduced earlier, the average time cost is 25 minutes. So this complies with our CI service level agreement. Note that for some critical tasks, Foster may block developers for the very severe cases. And for such cases, we have very low tolerance on false positives, which means Foster signal need to be very high quality to avoid developer frictions. Deploying code analysis at scale not only require solid technical foundations, but also good user experience. So we spend lots of effort to improve the dev efficiency by performing smarter reporting and with actionable signals. Its reporting pipeline contains the following major components. So first, we have a categorization component that would classify unique issues which would remove duplication and identify issues already happening on master. This would distinguish from the new issues. And then the categorization module classify. Then we have the localization module, which would analyze the collected traces and go through the call stack frames and try to locate a line that may be the root cause of the detected issue. And then we do signaling. This process helps our code analysis to prioritize signals and filter out known false positives. And finally, we have a fixed detection module, The automation is based on differential analysis based on the result across multiple versions of a diff. And this analysis helps us to understand the usefulness of our signals. Specifically for signal quality, we have a few features for reducing false positives and false negatives. First, we perform product matching. This means we map our detected issues to production logs based on the matched volume. We'll prioritize the signal accordingly. And the second, we perform continuous retrospective for the severe issues that we missed. And we ask ourselves, how could we catch this issue earlier? And third, we deduplicate the result from dynamic and static analysis, and we boost the signal when both analyses found issues with the same root cause. Finally, let me summarize. I presented our overview of code analysis tooling at WhatsApp, including several already open sourced. For dynamic analysis, I showed an example system named the Fosta, which is a privacy-first spec-based traffic generation system. And for static analysis, the example system we deployed is Infer, which analyze our code for checking reliability issues and user-specified properties. Both systems have been fully integrated into Meta CI pipeline, providing fast diff time signals for shift left and DevOps capture. Thank you for joining me on this deep dive into the world of code analysis. And next we'll do a Q&A. I'm glad to answer any questions you may have about this talk. Thank you.